thank you for being part of this. Thank you for coming today, Olaf. We're really looking forward to your talk, which actually is about WebAssembly, I hear. So let's take it away and see what you have to say.
Thank you, Jens. So, my name is Ólafur Waage, and we're going to be talking about Sandbox Games using WebAssembly and C++ to make a simple game. Simple game. That's kind of the main point here today. So yeah, as Jens introduced, my name is Ólafur Waage. I am a senior software developer at Turtlesec AS here in Norway. You can find me at Ólafur W on Twitter, while that's still a thing. I'm also on Mastodon, which is also one of those things. You can yell at me afterwards. I work for Turtlesec AS. We are a consultancy and training company. We do all sorts of consultancy work. We also do trainings at conferences. So if you are at C++ or similar conferences, you might see trainings by us. So if you do see them, please join and also talk to your companies about trainings. It's been kind of a theme year for me to have these philosophical quotes in the beginning. And I like to have these philosophical quotes to start with. And here we have, I must go forwards where I have never been, instead of backwards where I have. And that's, of course, Winnie the Pooh. Winnie the Pooh. Lovely guy. So let's do a little what this talk is and what this talk isn't. This is not going to be a game development talk or a game design talk. So a while ago, how this talk actually started to, how this talk came to be, I was making a game using WebAssembly and just figuring out what's going on, what these things are. And I hit my head on a whole bunch of walls along the way. And I kept notes, and these are basically the notes that I from that session or the sessions. This is also not a comprehensive talk about WebAssembly. That was another thing that I found when I was going through WebAssembly is there's a lot of talks about it, especially C++ and WebAssembly, but those talks are very in detail. Like one person took, I think, GCC and converted GCC to WebAssembly. So they're very like nitty-gritty details. This is more pragmatic. This is more, I want to do a hello world. I want to have a little project. Where do I go from here? And what you'll get with this talk as well, there's a bunch of links at the end. You'll get a bunch of like simple, small starter projects in various stages of development. So you can pick and choose and look at or adapt to your needs. Yeah, thank you for talking about people liking the test slide. That's very good. So yeah, the idea to be pragmatic, learn what this tool has to offer, because like with anything else, this is a tool. WebAssembly is a tool like anything else. So let's look at the problems it can solve. So let's start with, what is WebAssembly? How can something be neither web nor assembly? Because WebAssembly is a binary format. Yeah, kind of an asterisk on that one. Because it's designed to allow for performant execution of code within browsers. That's kind of the initial idea. It was announced in 2015. We have a working draft in 2018, a W3C recommendation in 2019. So it's relatively new, although like the history of it is a bit longer than that. And a nice way to think about WebAssembly in the beginning is think of it as the target output of any language. It doesn't matter what the language is. WebAssembly is a target output. And even in recent times, you can execute WebAssembly outside of the web. So again, it's not necessarily web, but it's a type of execution environment, if you think of it that way. So the text version of WebAssembly kind of looks like this. You have a function called add. It takes in two parameters, here called 0 and 1, and it returns an I32. So you can see that it has types, it has names for functions, it has some sort of, maybe you can think of it as scope. You're adding two numbers there, so you're fetching the local variable of 1 and 0, you're doing an add, and it's a stack-based language. So the last thing on the stack is the thing that is returned. So the last thing on the stack here is an I32 add of these two local variables, so that's the thing that's being returned. So if you're reading through WebAssembly, that's kind of how you read it. And we'll see way more complicated ones. And this is this function, basically. we're adding two numbers together. Cool. Okay. So many of you might associate WebAssembly with games, and even this talk is going to do that. WebAssembly is so much more, and you'll see what it has to offer. I use games mainly because it ticks a lot of the boxes that you might want from an execution environment. It's executing code, it's doing something visually, it's maybe getting input from files or keyboard or mouse or whatever. So it's ticking all these boxes, but don't focus on games, even though we're going to do that here today. So here are some examples that you might not think of that are written with WebAssembly. Windows Calculator. So someone took the code for Windows Calculator and converted it to WebAssembly. I think Microsoft open sourced the calculator a few years ago. And someone just made a WebAssembly executable from it, and here we are. That's the calculator. You might have heard of Figma uses WebAssembly. If I remember correctly, the whole thing, like the whole website thing, is not WebAssembly, but there are parts of it that are WebAssembly. So this whole thing is not WebAssembly, but a lot of things that are happening here are. Someone made like a Photoshop-like application in WebAssembly, and then later I heard that Adobe might be doing something like that, or are doing something like that themselves. So you can make an application like this. And again, it can just be the code. So TensorFlow.js, the machine learning libraries, has a WebAssembly backend. So that's been pretty performant as well. Here is, I think this is protein folding, if I remember correctly. So there was a website that does like these protein foldings, and you can lend your computer to help with protein folding. And they converted some of their stuff to WebAssembly and got a 20x speedup. The 20x speedup is pretty high. So don't expect, if you convert your stuff to WebAssembly, to always get a 20x speedup. I'll show you some caveats later on with that. So let's start with Emscripten. So what is Emscripten? Because this is WebAssembly before WebAssembly. So we originally had asm.js from Mozilla. It had similar goals to WebAssembly, to run efficient code on the web, but it was a subset of JavaScript. So you would take your low-level code, compile it with asm.js, you would get JavaScript out, and that's the thing that would be executed. And that's where Emscripten came to play initially, was to help with converting your lower-level code into asm.js outputs. And Emscripten is the tool that we will then be using, because it can also target out WebAssembly. So Emscripten is based on LLVM and Clang, so that's the toolchain you have. And you can get many different types of outputs. The files are called wasm files, or .wasm. You will also see .js or JavaScript files and .html in this talk. So let's go over the installation process. So if you were going through this and wanted to set this up yourself. So in this example, we're going to use VS Code as the editor. I'm using WSL2, using Ubuntu 20. Here's the code. If you want to take a screenshot and look at it later, it's on my GitHub called Talk ACC WebAssembly. So you can do a sudo of your favorite package manager, which one that is. We at least need Python 3, CMake, and Git. That's kind of the base we need for this. We will clone the Emscripten repo called emsdk. We can go into that folder. We can do a git pull for good measure, or if you're doing this later on. There's a script there called emsdk and install latest, and this will then install the latest version of Emscripten into your machine. It's a similar setup on Windows as well. There are similar scripts. So, and this will take a little while, but don't worry there. And then you activate the latest. It's one of those where you can have different versions installed, and you can switch between them if you want to do that. And there's also an emsdk environment script. You can source it now, or you can put it in your bash RC or something similar, or put it in your path in Windows. Yeah, there's a similar one for Windows as well. What this will do is this will bring the Emscripten compilers into your path, which is kind of handy. So you can say EMCC version, and you will get this kind of output or something like this. You can say Emscripten is a GCC Clang-like replacement and some information. And I can also say which EMCC, and it's in some home folder that I have, just EMSDK, and then the script is there somewhere. Okay, so now we basically have most of the things that we need to start developing. So what should we do? Well, it's the time-honored tradition, right? We're going to do a hello world, right? But there's a couple of more steps. There's a few things that we have to think about. So this is the hello world I'm going to do. I'm doing it in C, just because I thought that was a funny way to do hello world, because most of the rest is C++. But yeah, here's C, include studio, printf hello world, and return 0, right? I can compile it like this, emcc hello world C. It will compile, everything is happy. The output you get looks like this. You have aout.js and aout.wasm. Okay, so what is this? What can I do with this thing? Well, not much. What you can actually, if you have an application called Node.js, you can actually run aout.js, at least in this state of the application. But we want something else. We want something more. And what you actually do is you say emcc hello world.c, and you say that the output is going to be an HTML file, which is pretty weird for some, I imagine. And what you get is a hello world HTML, and then the two files from before, the JavaScript file and the WASM file. So yeah, we have an HTML file, we have a browser, so let's open it. Well, it's pretty long. It's 1,300 lines, the HTML file, and the JavaScript file is 2,400 lines. So what is this? What are these files? What are they doing? Because this feels like magic, right? I get some WASM file, and then I get two huge files, and I'm not happy with that. I want to learn why. What is this? What is this doing? So let's do that. Yeah, with Node you can run the JavaScript file just fine. Yeah, let's open the HTML file. Should be no problem, right? No. So this is the first wall you will hit, because of course there's a problem. Browsers don't like opening random files from whatever location you decide. That's a thing. There's a thing called cross-origin resource sharing, or CORS. So by default, browsers don't like loading external files from disk, because if you double-click on the file, it's going to open the HTML file fine, but all the external dependencies, the JavaScript file that we made, the .wasm file that we made, they are external files on disk, and the browser is not going to allow you to open them. So what you then need to do is to run a web server. So for hello world, yes, you need a web server. So Emscripten has a tool called emrun, and we will use that tool for a few of our examples. It's a very, very basic web server. So it's fine for development, but as soon as you get a little bit more complicated, you need to replace it with something else, like an actual server or some development environment. But to begin with, emrun is fine. It will do your thing. You can run it like this, emrun, you give it a port, you say hello world.html, and it looks like this. So we have our little hello world. I can resize the canvas, and you can see, so this thing in here in the middle is the canvas, and here is the output. So if you have any printable output using printf or cout or any of those things, when you're running it and developing and refreshing and doing that iteration, you'll see the output there. So hey, we have hello world. We should be happy, right? Okay, so let's look at the game we'll be making. And because I talked about that this isn't going to be a game development talk, I'm not going to go into super detail of how the game is made. Just we're going to look at how it works, and you can look at the code afterwards and play with it. That's totally fine. You get full source code access to the game. So the game we're going to make is a simple sliding puzzle game, similar to games like Threes and 2048, if you played those games. So it looks like this. So I can press up and down on the keyboard, and new boxes will appear. But if I then slide, for example, to the left, those two boxes will join, if I slide down, the 2s will join and then the 4 will join. And every time you do a slide, a new box will appear. So you can you want to try to create like a really big number. So here I got a 16, I got a 4, I got the 2 16s. Now I can slide down to join those 2 16s, etc. That's the game. So we have something visual, we have some code, we have some state, we have some input that we have to deal with. Okay, cool. So let's convert this game over to WebAssembly, because currently this version of the game is in JavaScript. It's only JavaScript and HTML and nothing else. So there are 2 ways to do this. We can keep the drawing part of the game in JavaScript and do the logic and the state management and all this in C++, or we do everything in C++, even the drawing. And we're actually going to look at both, and we're gonna hit some more walls on the way. So let's look at some of the functions. I mean, if you're converting stuff over, let's look at the stuff we have to convert. Okay. Some of these functions that we have, even in the code, don't even need to know about game state. They're just general utility functions. So let's start with them, right? Sounds like a good idea. So here's 2 functions in the JavaScript version. We have a get random coordinate. So when I create the new box, we need to find a random place to put the box. So I get a random coordinate. And I can also ask the question, are you outside of the box? Which is just, is the X bigger than the length of the board? So I'm just testing so you don't go outside of the board. So these are pretty simple functions. So let's create the C++ version. So here I include Emscripten.h. So after you installed Emscripten from before, you should have access to Emscripten.h. I create a context per variable of board size. I create a function called isOutbounds, takes an X and a Y. The body of the function is the same. We have a thing there called Emscripten keep alive. You'll see why we need this in a second. And I also do an extern C. And the reason for extern C, is because we need to access these functions from outside of the WASM file, because we don't want the name mangling to happen. So we say extern C of the functions. So it's only for the functions that you want to expose. So basically think of this as the things you want to export. And this is the whole file. This is the whole thing. And this is the thing that we're going to compile. And this is why we need Emscripten keep alive, because this is the only function that's in the file. There is no main function, and there is no function calling this isOutbounds function. So we need to prevent that the compiler will actually optimize away this function. So that's why we have Emscripten keep alive. These are just different ways to prevent the compiler from deleting our function. We compile it this way. So emcc and -g. -g source map, you'll see why in a bit we need that. We say no entry. This means that there's no main function. I also say -s, standalone WASM. And this is the thing where I want to make this HTML and JavaScript file myself. So it will only give me a .wasm file, and all this other stuff I have to make myself. I give it the name of the file, and I say GameLogic HTML. And we're not going to use that HTML file. We're going to make our own things. So because we want to know how this works, we want to learn what this is actually doing. We make our own HTML file and make our own JavaScript file. And in our JavaScript, we do this. We say import object. This is just an empty object. We call WebAssembly.instantiate streaming. We call fetch on the GameLogic WASM file. And this will then load the file into memory. And we give it an empty import object. And at the time, I had no clue what this import object is. So let's learn what's happening here. This is an asynchronous function. So I do a .then, and I get results out. And within those results is the instance of the WASM file. And within the instance of the WASM file are the exported functions. And within the exported function is our isOutbounds function. And what I can do in JavaScript, then I can say var isOutbounds is equal to this function there. And then I can just call the function. So I can use is_outbounds like a regular function. I can give it 2 arguments, and it will do its thing. And here we have WebAssembly running, and it's just this one function and nothing else. So cool. We are happy. We are moving along, breakneck speed. So let's do the next one, right? We did the first one, and now we're going to do the next one. So the next one is get random coordinate. This is to find out where we are on the map. So it says math.floor and then math.random. Okay, cool. Seems simple enough. No, it is not simple enough, because where we are going, there is no operating system. So this is kind of the idea of the sandbox that we have. Because with the standalone WASM file, there is no operating system level functionality. It is only that file and only that one function that we wrote into it. You are all on your own, kinda. So how do we solve this problem? So if you want to use random, if you want to call timer functions, many other operating system level functionality, it has to come from somewhere, right? So thankfully, there is a solution to this, where if you build that JavaScript file that we saw before, in addition to your WASM file, that JavaScript file is your gateway to the operating system, if you think of it that way. So you can actually then call functions on the C++ side over to JavaScript. JavaScript will do its thing. So you have exited the sandbox. JavaScript will do whatever it wants to do, and then it will come back into the WASM, and then you get your results. And so kind of think of it like a syscall that's happening here. But instead of being a syscall in an OS, it's a syscall where you're going to the JavaScript world and then going back. But yeah, how does this work? Can we do it ourselves? There's a function within Emscripten called Emscripten random. And this is just after I was Googling, like, how does this work? And it will generate a random number between 0 and 1. And it says here, this maps to math random. Okay, this looks great, but how do we use it? So what I did was I just said, okay, get random coordinate, return Emscripten random, right? This compiled. I was happy. I'm like, okay, let's change the JavaScript part. Here you see the whole HTML file. I just say same thing, import object, it starts it streaming, I get the results, I get the function, and I would like to print it out, console log. Like, what happens when you call this function? I mean, it seems sensible, right? But no, it doesn't work. So here it says WebAssembly instantiate, import, module env, error, module is not an object or a function. And this error kind of doesn't make sense if you ever happen to encounter it. And what it's saying is that this import object here, that's the important bit. Sorry if you can hear my cat snoring. I hope that's okay. She's sleeping very nicely, I think. So this import object, this is the link between the WASM world and the JavaScript world. So it was asking for an object called env. So I'm like, okay, let's put an object called env in this import object. Does that work? Does it change anything? Well, yeah, it changes the error message. It says module env, function Emscripten random, error, function import requires a callable. Again, this doesn't make sense. So what's actually happening is, if we now look at the WASM, so this is the whole file. There's nothing else there. In this example, I didn't have the other function just to simplify what's going on. But we've only, like the thing I showed you before, is we've only looked at this part. There's a function, it's called something. This one doesn't have a return value. And we do some work, but look at this line over here. We say call env Emscripten random. So what is that? So the thing that we haven't looked at in the WASM file is the top part. So you think of the top part as the module definition or the header or something like that. And you can see that on the second line there, we are defining that there's a function called env Emscripten random, which is going to be imported. It's going to be in an object called env. There's going to be a function called Emscripten random, and it's going to return a value of f32. Okay, so what this actually means is there should be a function here. So in the env object, on the import object that you give to the instantiated streaming, there should be a function called Emscripten random. So here is the actual then implementation of random that our WASM file is depending on. So again, think of the OS level connection here. The WASM file needs random. It can't implement random, or like it doesn't implement random. We need random in some way. We go out to the JavaScript, we call a function, and then we go back. And yeah, this works. You're happy here. And this is what the JavaScript file is doing. This is why it's so long, because it's figuring out what are all of the operating system level things that you need from the outside. Let's fill in the JavaScript file with everything you need. So yeah, that's kind of the heavy lifting that Emscripten is doing for you, and other tools. Like it's not just Emscripten. Okay, so now we can move over to the rest of the logic. The board is an array of arrays, of boxes, and the rest of the game logic is basically identical. I can show you in a bit. So now the gameplay can be simulated and called from JavaScript, but now we need to draw the data. So we actually converted all of the functions over. The game state is iterating, it's doing its thing, but I would like to draw the data on screen. And that's the next issue point. Where's the data? Because now I have a state in a WASM file. How do I get it out? So we can communicate between C++ or the WASM and JavaScript using primitive types, like you saw before. But soon as stuff gets a little bit more complicated, you are in a bit of a trouble. You could actually view the raw data of a std vector. Let's say you have a std vector in your C++ side, but that doesn't mean anything to JavaScript. Like the list in JavaScript and vector in WebAssembly don't match. They're not the same data type. There is a thing called embind that helps us with passing these more complex objects. So here I'm describing a class, and I'm describing how does the constructor look, what are the functions, the properties, the static functions, and you could do this to your types. There's even a thing called so embind has utilities also for vectors. So you can register a vector. You can say like, there's going to be a vector. It's called this. It looks like this. So then you can send the vectors back and forth. You can even define a shared block of memory that can be used by either JavaScript or C++. There's even an option to return a pointer. You can. Yeah, be careful, please. Yeah, you're in territory where you need to be a bit more careful. But WebAssembly actually has some guarantees about like assumptions about the execution environment. Like the bytes are 8-bit, addressable at the byte memory, underlined memory, two's complement, IEEE, little endian, those things. So if you want to do like these more finicky things, it has these kinds of assumptions that you can take. So like with any restrictive execution environment. So at least in this case, yeah, thankfully, I wrote the game logic with basically primitives. So I can just send ints and floats back and forth. So let's look at that version of the implementation. So this is actually that version of the game. It looks the same. But the logic of the game, where the pieces are, where they're moving, all this stuff, that's happening in WebAssembly. But the drawing is happening in JavaScript. So the calls are going back and forth. So there's a lot of calls happening here that are going back and forth between WebAssembly and C++. So it's not slow. Like you don't have to be super worried about this. There's one thing as well that you might be thinking of, like how am I doing this? Like how am I playing the game in the presentation? That's because, did I not click here? The presentation itself is also written in WebAssembly. That's a bit of a twist here. So I wrote a little slide application thing in Rust. So I have like this slide parsing code in Rust, and then I have the actual slides here in Markdown. And then in the Markdown, I can actually do an iframe of the game, and the game is actually running here. So all of the games are running here in the background. So I have all the examples running ready, and the slides are just showing the iframe of the thing. And I thought there was just a fun way of showing you other ways that WebAssembly can be helpful to you. This is called using a library called, I think you say U, it's YEW, which is in Rust. And you also you can get access to this code as well if you want to look at it. So that's what's happening here. Just a little fun example. Okay, so this is working. I can actually show you here. Let's go back to this. It was. Let's have this URL here. Go to the actual page. So this is the web page itself. Let's go and dock this down here. Also, because if you're thinking of like development and how you are working with this whole thing, so here I have the game. It's in this like little canvas block over here, and I can play the game. You have console output, so if you want to print things, you can do a console output thing. With the sources, and this is, so it's working for me here. In some of the situation, this was a bit finicky, but you can do this. You can actually get the CPP file itself. So here I have, here you can see the get random coordinate is out of bounds. There's another one for is empty, and you can ask the box if it's mergeable. Yeah, like the actual CPP code is here. And if I put a breakpoint here and then move the game, I hit the breakpoint and I can see the actual values, the local stack, and I can see the callback, basically the call stack itself. But what this is doing, remember when I said when I'm compiling, I say -G and then source map. What's happening is I'm actually putting a breakpoint in the WASM file. So in the WASM file is the breakpoint. It's just mapping that line 54 in GameLogic CPP is line whatever in the WASM file. So that's actually what's happening. So yeah, it should be, it's a pretty long file. But you can see like you can also get the file itself here and then look at what's happening. And you can see also like we have the game running. Still, the only thing that we ask for from the external environment is the random function. It's going to fill up in a bit, but it was fun that in this case, it was only the random function. So I didn't need anything else. Yeah, breakpoints is really cool to see. I can put them in any file. But note, like I had some issues that sometimes the CPP files wouldn't appear. And it seems to be about how you host the web server and where the paths are. And yeah. But yeah, we can do then continue and then continue playing the game. And also because this is Chrome, you have the network tab if you do any networking things. You have the performance tab, so I can go here and play the game and hit stop. And I get, let me see here. Oops. This is interactions. Here, let me make this a bit bigger. Here are the calls. So I can get the, what's it called, the flame graph or whatever people call it. So here's the main function. A lot of gaps here between, but yeah, you can see all this stuff. And the cool thing also is you get the screenshot of the game and you can be like, oh, it's over here. Here's the problem. Okay, let's click there and zoom in. Ah, I see the problem. This is taking too long, or whatever the problem is. So you have Chrome's developer tools and performance tools. You get them for free, basically. Same thing for memory. You can take heap snapshots and all these other fancy things that Chrome has. And same for Firefox as well. What happens if you modify code when it's running? You have to recompile it. So you need to, because what you're actually running is the WASM file. So unless you're able to modify the WASM file while you're running, so you have to modify the code, recompile it, and then Now I see the potential of Google Chrome, my least favorite browser. Well, it's the same in Firefox if you want to use Firefox. So if Firefox is your favorite browser, you can also do it there. I haven't tried Opera, but I also hear that it's the same thing. Same thing there. So development, that's kind of cool. Okay, cool. So now we basically have everything except the rendering in C++, right? So let's move over the rendering, because before, I can actually show you, maybe I can show you the project as well, since we have time. We have plenty of time. So this is the project that you can look at later. It's numbered based on where we are in the process of converting the project. So one JS canvas is the whole game in JavaScript only. So here's just a simple, let me make this a bit bigger, simple HTML file. You have the game, you have an update loop, you have a draw function, you have a main where you're like queuing up calls every 60 seconds, getting a canvas context and listening for keyboard events. And yeah, it's a very, and then you have the box logic of the boxes moving around and doing their thing, if you want to look at this later. And then there's within each folder, there's always a little script hinting at like how you can run this. So here's how you run this one. Here's the hello world. Then you also have how you can run the hello world, how you can build the hello world. And then we're here now in 3. So this is Wasm, but with only game logic. So we have our box in C++. We have the game logic in C++, the thing we looked at before. And you also have the run script, and you have the build script with all the commands you want to use. Yeah, here's the G and G source map. And again, we're doing no entry, we're doing standalone Wasm, so we only get a Wasm file out. That's the only thing we get. And then, yeah, there's more in the project itself. All right, so because now we have the game logic in C++, we have the drawing in JavaScript, let's move over the rest. So let's do everything in C++, and the JavaScript version does basically nothing or very little. Or at least the code that we write for JavaScript, it does very little. Okay, so thankfully, Emscripten has great support for exactly what we need. Emscripten has built-in support for a thing called SDL, which is a cross-platform library that provides all sorts of things. The thing that we actually need is graphical rendering. It also does audio, it does input, it does lots of great things, and it's usually used for games. It has SDL1 built in, but for SDL2 you need to download it. And there's also there is a script to download. Because there is kind of a chicken and the egg problem with SDL, that if you don't have SDL installed and you make a project that requires SDL, it doesn't compile because it can't find the stuff. So there is this kind of what I call a first install script that is an empty CPP file, but a build script that says, hey, we require SDL, which will download the SDL, and then you can just delete this. Okay. Yeah, and these are the commands. You just add these to the build commands. And because we are using SDL2 and all of those related functionalities, and we have now learned how this works, because we've learned what the JavaScript file is doing. It's providing the operating system level functionality to us. The HTML file is just holding everything in place. So then we're okay with using the JavaScript code it generates. So we're going to do that. We're no longer going to be Wasm standalone. We're going to let Emscripten generate everything for us. So yeah, instead of creating the import object ourselves, Emscripten is going to do this for us, and I can show you that file in a bit. This also means that our game is going to need the main function because we are no longer standalone. And here we have some information. If you have a canvas and you do an SDL create window, it will create the window on the canvas in the thing that you are actually displaying, so in the XML file that you have. But this line here, the bottom line, is the one that I'm most interested in because we don't want to hog all of the kind of the resources or the time. So what we say is there's going to be a function called game loop, and we're going to tell Emscripten, call this loop as often as you can. So this is going to be your loop. Because otherwise, if we call main, it's never going to exit, and the browser isn't going to get any time because they share time between each other. So I poured over the rendering code. It's very, very simple rendering code. It's let's actually show you real quick. We go here to game logic. It is this. I create a rectangle, I set the color, I draw the rectangle. That's it. That's the code. Oh yeah, okay, no, I remember now. I had the examples. So drawing is we create a texture, we set the background color for every row in the board, and for every box in the row, we draw the box, and then we copy the texture, and then we clear the texture, and then draw looks like this. That's the only thing that's happening. So I create a rectangle of a certain size, I set the color, and I fill the rectangle. And the texture is just an image, and I say like put a red rectangle here, and then every frame I'm changing where the rectangle goes. So it compiles, and in the beginning I'm only interested in the box. I just want to see the box. I'll do the text that goes on top of the box later. So just the box right now. So it compiles, looks like it should. I run the code. I see the box. Okay, great. I look at it for a couple of seconds, and then, boom. Runtime error, aborted. Cannot enlarge memory arrays to size, and then some certain size. And it gives me some hints there. So what's going on here? So wall number 4. The sandbox isn't infinite. So up to this point, we've been using the default memory size from Emscripten, and it just happens to fit. But we need more memory now since SDL is involved. We need to create textures, we need to create images, and that kind of thing. So there are a few things you can do. These are just, again, command line arguments you can add to the build step. You can set the initial memory to a certain size. You can say that the total memory is a certain size, and you can also allow for memory growth. So you have some flexibility there. You don't have to use all 3. I use all 3 just to show you, but you can pick. So again, this compiles, and now we see the box. Okay, I just changed the size to something bigger, and we're happy. The next step is then to draw the text, because it's a 2-step process. First we draw the box, and then we draw the text on top of the box. Oh, no, that's wall number 5. File not found. Because the environment we are in, it also doesn't have anything else except the WASM file. So we have the WASM file, we can communicate with the outside world, but there isn't much else. So the font file I want to use, in this case I think I use Arial or something similar, it doesn't exist. Because what is a file system in a sandbox like this? So we have to provide the files in some way. We have to tell the sandbox, hey, there's going to be a WASM file, and there's also going to be another file over here. And what you can do is you can do this. This is another compile step. You can say preload file. I point to a folder. I say then and then /assets. So I'm saying that there's going to be a folder over here, and then pretend that the path to it is the second part. This then means that within the C++ file, I can say this. I can say /assets/Arial bold, and that's the file. I can open that file. There are 2 ways to add a file. You can either preload the file, or you can embed the file. So the file is embedded in the whole thing. Emscripten also provides a bunch of helper utilities for common development tasks like make and CMake. So I also wrote a simple CMake file. So in the 4th project, we have CMake. These are no longer just bash scripts. We actually have full CMake for this. But for CMake, you have to say, like if you want to say make, you have to say em make. So you do that twice, em make, clean, and then em CMake, or em make. These em files, these are Python scripts that help, they set up the environment for you. So you know which make to call and give it the correct environment variables. And then, you have a CMake file. So here's an example. This is the one we're using right now. We create a project. We say the executable suffix is HTML. We give it the files. I create the flags. And notice fsanitize address and profiling. This is how we got some of these warnings that we got before. So you can use address sanitizer, you can use undefined behavior sanitizer, because, like I mentioned before, this is based on LLVM and Clang. So those tools are there and you can use them. I can even optimize, do an O2. This here source map base, this is one of those ideas where you can point to where the CPP files are. Again, it sometimes works, sometimes doesn't work, but that's an option for you. Yeah, and then STL and the memory, and then you link these things together. So that's great. So yeah, this is great. We have everything running. So let's look at it in action. Here's the game. For those with keen eyes, might notice that the font isn't. It's more jagged on the edges because I don't have the anti-aliasing enabled for the text. But otherwise, yeah, it's the same game. I can press all the buttons and do all the things. And what's happening here then is we're pressing buttons on the JavaScript end. We're sending those button presses to the WebAssembly, and then we're getting the texture is being drawn on this canvas via STL, basically. So yeah, everything is or mostly everything is on the WebAssembly end. Cool. So let's summarize the walls that we have encountered. Files need to be served while developing. So if you think about the hello world, you can't open random files, so you need to have some sort of server. All functionality that you depend on, OS level kind of things, they need to be implemented in the JavaScript, in the WebAssembly file, or they need to be given to you through that path that we saw. Data needs to be primitives or converted in some way, maybe for example through the embind or those things. Memory size and growth needs to be thought about, and any files that you want to use need to be embedded or preloaded with the output. One more thing, right? You always need to have one more thing. So in the project you have, let's finish looking at WASM 4. So here you have the CMake file. This is the same as we looked at in the presentation. This is the first install stuff, so you can just run the bash file here. The index HTML, it doesn't have much. The most things it has is the key down event, so we can send the keyboard input. The build script is just using make and CMake. You can see that the assets are here, folder called bold.ttf. Maybe interesting on, yeah. So here's the WASM files and the maps. And the server is a bit different as well. It's just another example of a server to show you. For this one, I'm using Python, and I'm using the simple HTTP server thing that Python has, just to show you another way that you can host these things. One change I did was I changed that if it's a WASM file, I do a different request header, but otherwise, yeah, this is the same. Okay, so one more thing. Can I open? Who wants to play Wordle? Isn't Wordle the cool thing now? Okay, we're on a bit of a delay, so I'm gonna play Wordle. Can I do what's a good four-letter word? Spots. Many spots. Okay, we have an O. Maybe it's over. Starts with an O and has an E. Well, maybe we can do inspect, and we can just cheat. Omega. Oosh. I'm so good at Wordle. So I also implemented. So this is another way of doing a game. Within the project, you also have Wordle. So if you want to do that, so this is just Wordle the game. We also have a Wordle bot. So so people don't get if you don't like the blinking lights. So I'm going to show you again for a real second if you want to look away. So we have a bot that plays Wordle, and it's trying very greedily to solve Wordle by reducing the number of words that can be in the set. And we win about, it seems to be just under half the games, or about just under half the games. And we can play about 30 games a second. Okay, this sounds interesting, right? So let's look at the WebAssembly version, because I also converted it to WebAssembly. If I go here and I open extra, and I build it. Yeah, I can show you here. So I'm building that behind the scenes. So that built, I can do run. So open the browser, let you see that for a little bit, and I can close the graphics. So this is, except the drawing part, this is fully in WebAssembly. But do you notice a thing? So if I go here to the JavaScript version, we're playing about 26 games a second in the beginning, playing about 30 games a second. If I go back here, again, it's playing about 30 games a second. Why isn't it faster? Is the question you can ask. I now converted the thing over to WebAssembly. People talk about WebAssembly being faster. Why isn't it faster? Okay, and I'll show you why. So there's a thing that's happening here that we saw here before. If I go back to performance and I do a recording of the performance, I play the game a bit and I hit stop. Remember, if I make this a bit bigger here, remember these gaps between, because we're executing some code. Part of the execution of the code is the execution of the WebAssembly part that we had here. So 0.11 milliseconds. We do some task related to probably graphics and compositing and this kind of stuff. And then we stop here. So 726 milliseconds up to about here, 732 milliseconds, where we do it again. We do a main, we do a draw, and then we go again. So here's the thing. Browsers have frame rates, if you didn't know. And because browsers have frame rates, what we are doing, if we look at, for example, this one here, how we did the graphics here, we have a function called main. We're asking for an animation frame from Chrome. Then we do some work. And when this starts, we say, when you are ready to draw something on the screen, dear Chrome, call this main function. So that what we do, we say, hey, call the main function. We do our stuff, we update, we draw to the screen, and then we come back and we say, hey, when you're ready again, draw. So this code over here only runs once every 60 frames or 120, 144 based on your screen. So our wonderful, it's one because I've been alt-tabbing away. This solver that's over here only gets to solve a game once every 60 seconds. The same thing with this one. It only gets to solve a game every 60 seconds. So what you then have to do is you have to say, either thread things or say, when you're going to solve a game, solve as many games as you can in the allotted time. And then when you're out of time, hand over back to Chrome and then give Chrome the information. And then Chrome might draw something. And then Chrome gives execution back to you. You try to solve as many games. But this implementation is draw a frame, solve one action in the Wordle, draw one frame, solve one action. So this is another thing that you have to think about if you want to have some performant code, is you have to do either some threading or you have to basically be aware of this limitation that's there. So this Wordle thing is also there. If you want to look at it, it's these extra 1, 2, and 3. So Extra 1 is just the game. Extra 2 is the Wordle bot in JavaScript, and extra 3 is the Wordle bot in C++. It's a very simple and very greedy bot. So if you want to optimize it as well, you can do that. And it has all the build script and everything as well. So please enjoy. Let me then go back to the presentation. No more Columbo. And that's me. My name is Ólafur Waage. You can yell at me on Twitter or Mastodon. And these are the two links, the ACSU WebAssembly for the code that we've been looking at, and the WebAssembly presentation if you want to look at the Rust thing for the actual presentation. And yeah, then that's me. Yeah, I think it's an hour.
Thank you for your talk. That was pretty awesome. Good introduction on how to get started with WebAssembly and do some C++ with it.
Thank you.
So if you have any questions, you can share them in the Q&A tab or in the chat. And I'll be reading them and maybe copying them over.
I can see them, so you don't have to.
Okay, yeah, but still for the video purpose.
Okay, yeah, good.
But right now, yeah, someone's saying very cool. I agree with that. And there's the first question.
Is there a limitation on using threads? So threads were very recently standardized within WebAssembly. So WebAssembly is a sort of standard. So there is like there's a proposal, there's a version. We have a version 2, I think, coming up at some point. So for a while, it was only Chrome that had implementation of the threads, because they had this experimental extension of threads. And then most other browsers did follow suit, and they implemented threads in the same way. So it has just the same issues or limitations and all those asterisks and warnings you have with normal threads is that you have to think about. I haven't played with them a lot, but yeah, they are there and you can play with them.
Is there a wall on linking to dynamic libraries?
So I don't know what they mean by wall, but regarding linking dynamic libraries, think again around the environment that you're in. Where the WASM file is, and then the WASM file that you're looking at, maybe it's a nicer way to just show it this way. Yeah, the thing is still shared. If I go to sources, here's WASM. This is it. When you load a WASM file, this is the file that is loaded. This is the code that you have on your hands. And if you need anything from the outside, they are described here. Maybe it's cool to, if I go, let's go to the slides. I'll show you the full C++ version. And you can see that I had issues with getting the CPP files here, so they're not here. But if we look at the WASM file, this is kind of maybe a fun thing to look at. Look at the things that it's requiring. There's a bit more. It's a little bit more. It's not until here that we're done. So all of these things that we're asking from the outside, a lot of them are graphics related. It's asking for OpenGL kind of graphic stuff, and that is implemented in Emscripten through the use of WebGL. So that's one library that you can be using, for example. So here we have like terminate and WebGL, and we have some gamepad information and all this stuff. So if we go to here and look at the game.js file, so let's find one of these functions here. Emscripten GL blend color, classic function. So here it is. We can find that it is in a map. So Emscripten GL blend color is calling a function called underscore Emscripten blend color. If we scroll up here in this map, the ASM library argument, go down here, here is an object called info that has env. This is the thing from before. This is this object here, info, that is then being sent into WebAssembly as instantiate. So this big JavaScript file that we had before, it's doing the thing that we looked at before. It's getting the binary and being given this info, and info contains this awesome library argument. If I look at that one here, and let's look at again, Emscripten PL color mask. Let's find that function. And it's just calling, this is WebGL. So it's calling the WebGL functions. So this is the environment you have. So this is the code you have. This big file over here, this is all the code you have. And then you have connections to the JavaScript world. If you need something else, it either needs to be here in the WASM file, it needs to be another WASM file, then you have to communicate in some way, or it needs to be in the JavaScript world. So, yes.
Yeah, I think a good place to look for like how to handle dynamic libraries might be the Qt port for WebAssembly. You know, we've had it mentioned as a question on social media, but
yeah. So an important thing maybe to think of here, like I'm showing you how it works and how very simple projects are made. When you go a bit further, it's really nice to use solutions and libraries made by others, like what if Qt's doing, or if you're using Rust stuff, or any of these other things that you're going to use. But then if you have a problem, if you're stuck somewhere, you know how these things are wired, you know what's happening behind the scenes. It might look a bit more complicated, but this is what's happening. So I recommend looking at this way and playing with the project. But then if you want to go further, it's nice to use utilities made by someone else. Here's one. Is WASM a go-to solution to porting over a 20 megabyte application? I haven't done really big applications. I've mostly ported or made like smaller games. If at any point you're at a conference and you can ask Adobe what they're doing. But what I know is if you want to have something on the web and you want to have, let's say you have an existing C++ code base and you want to use the same code base, but then target web, right? You might not want to expose your entire code base to WebAssembly. The web application might be its standalone thing, but there are these few things that you want to use, maybe some algorithms you have, or some functionality that you want to have in the same code. Then you can just target WebAssembly for those functions, generate the WASM file, hook up to the JavaScript, and then off you go, right? But these really large applications, I don't know. It wasn't, yeah.
There's access to the whole DOM into the environment.
Yeah, you can do all sorts of fun things. Because like we showed, that the only thing that's happening is you're calling a function in JavaScript. What's happening in that JavaScript function? It's just a JavaScript function, so you can do whatever you want. Look at it's called URS. So this is in Rust, but there are, I think, similar in other languages. This is to create web stuff, like the presentation I had. This is WebAssembly. Like I can go inspect and go to sources. There's a WASM file here. It's very big. Here we go. And it has a lot of interesting things. But what this WASM file is doing is, this isn't a texture. This is HTML. This image here is just, I can right click and save image as, right? So yeah, you can do all those things. Can users configure resource limits, RAM threads? Yeah. I showed. It was in on. Maybe just show you the CMake file. So you have these initial memory and total memory and long memory growth. I think there are similar. I only showed these, like these -s or flags are for the Emscripten. There are way more. There's a bunch of others about like limitations and restricting and enlarging the environment. So there's a bunch of these. So look for the Emscripten flags for your compiler. And I think the thread limits you can set. You can even change how threading works. So you can say that from the C++ side, it looks like you're multi-threaded, but actually there's just one execution environment. I think it's called Asyncify. So that's kind of neat. Yes. Did we had some fun ones in the thread? Let me see. Super good.
Yeah, I think there's like a clarification on the question. Like users are meant to be users, not like developers. Like, can you configure the?
Can users? Oh yeah, sorry. Yeah, I read that wrong. Can users configure? I haven't looked into that. So yeah, I might want to look into that, and you can too. But from what I see, I think no. Like if we go here to, I think it is under application. There might be something here, but that might depend on, because you can mess with the service workers, or if you have any offsite workers, but yeah, not sure on that one.
Now I saw your drawing there a lot. I wonder if is WebGL related to WebAssembly, or is it something of its own?
It's something of its own. So the browsers are implementing like a GL-like thing. So it's its own.
So it's more like on the cover, on the canvas running then.
So here we have a beautiful little box. Yeah, it's on the canvas. Like on the canvas end.
Okay. I don't see any more questions, and these questions were very wonderful and good. So thank you for your time, and thank you for the talk. Very awesome. Like you use now both C++ and Rust for WebAssembly. What's like the difference for you when you wrote the slide tool in Rust?
Rust, because it has a package manager already built in. So a lot of the helper tools and a lot of the utilities are just there. So you can just install them via cargo and you have them. So the community is like slowly creating this little environment of these nice things. There's a thing called, oops, wrong window. A thing called trunk to bundle and ship your Rust WASM. So there's a really nice tool for that. And if I go to, I have, so here I have the repo for my talk, and then I also have the repo for the presentation. And this is the whole, or last time I tried it, this is the whole thing you have to do. Like from you don't have Rust until you run the presentation. This is the whole thing. So it's pretty nice. It's pretty nice. Of course, there's some teething problems, and a lot of these libraries are young compared to like, because you have Emscripten is a much older project, and it's based on LLVM and Clang, so there's a lot of history there, and you have a lot of these mature tools there. So yeah, there's you can take different aspects of it.
Sure.
Cool.
Okay, then thank you for your time.
Thank you, sir.
It was great to have you, and I'm going to end the stream now. And